Finding volumes. Yeah, you have all the good information, the background information, the formulas right up here, so we'll refer to them as needed. Okay, R is the region in the first quadrant under this graph for X values between 4 and 9. Typing that into the calculator, kind of zooming in because it's really kind of crowded and really kind of small. The graph drops like this. So let's consider this to be 4 and this to be 9, just to get a visual. Okay, if X is between 4 and 9, we can kind of build vertical walls there at X equals 4 and X equals 9. Okay, and it tells us in the first quadrant, so that kind of tells us that we're just dealing with Y equals 0, X equals 4, X equals 9, and the equation for Y right here. All right, we're going to find the volume of the solid whose base is this region and whose cross sections, okay, are perpendicular to the x-axis are squares. Okay, so if we're perpendicular to the x-axis, then we want to put our little strip here perpendicular to the x-axis. So these are cross sections. There's one of two formulas we can reach back and find. Perpendicular to the x-axis requires that we use this formula. Integral a to b a of x dx. And what we did is we said, well, the cross sections are in the shape of squares, so we need that geometric formula. And, ooh, I didn't put this in a good place. The side length of the square that's in that region is going to go from here to here. So 1 over the square root of x minus 0. So this top y minus the bottom y, so the difference of these two. Okay, let's dump everything back into the formula. Do I have my limits? Yes, I do. 4 to 9. Okay, the area formula is side squared, so when I put a squared here, it's integration with respect to x. So, and all I need to put in here is 1 over the square root of x. We can certainly calculate this without a calculator. It's not too difficult. Squaring this quantity, we get 1 over x. Okay, we can quickly see that we're going to go back to natural log absolute value of x. We're going to evaluate from 4 to 9. Natural log absolute value 9 minus natural log absolute value 4. We don't need the absolute values anymore, so we can just simply have natural log of 9 minus natural log of 4. You might see this stacked as a fraction using log properties. You might see it something like this. Very possible that this may be seen as 3/2 squared, because squaring each of these gives this. And then using a property, you may see the 2 is pulled in front, something like this. So there's various forms, especially when you come to natural log problems. All right, so we found the volume by cross sections. Notice there's no pi. Unless the cross sections have a shape of a semicircle, for these slabs, as they call it, okay, we don't have a pi unless we're dealing with a semicircle. All right, let's look at example 2. All right, let's get a picture. All right, so there it is. Y equals x squared, y equals 4. Find the volume of the solid generated by the graph bounded by these two equations. Got it. When it's revolved about the x-axis, so show the x-axis. Okay, you want to put in your rectangle that's perpendicular to the axis of revolution. Okay, and notice that not every single one of these rectangles is always touching the axis of revolution. For example, this rectangle, there's a gap between this bottom and the axis of revolution. So as you rotate it around, you're going to have a hole. So give yourself a little note here, washers. So this is revolved. That's not the slab problem. It's either discs or washers. So if it's washers, do yourself a favor. Get the setup. It's going to be pi a to b with respect to x. So we have x limits. Outer radius squared minus inner radius squared with respect to x. Okay, so the volume is equal to pi, and my limits are going to go from -2 to 2, because I can see that these are the x coordinates of the points of intersection. I can set these two equal to each other, these equations, solve and get -2 and 2. So the limits are pretty easy to take care of. Okay, now the outer radius. For washers, this is where I said stand along the axis of revolution, lining yourself up underneath the or on top of the rectangle. Okay, the greatest distance from where you're standing to the rectangle would be at the top of the rectangle. So that's your outer radius. All right, well, what's the length of that outer radius? Well, we typically go from top to bottom. So we're going to say it's y equals 4, 4. Okay, remember this equation is y equals 0, the x-axis. Okay, so it's 4 minus 0. That's your outer radius. 4 minus 0, square it. Minus, okay, now your inner radius, back to the axis of revolution, to the rectangle, this little distance, this shorter distance right here, is your lowercase r. Well, what's that distance? Well, to get that to be positive, I'm going to start here on that curve, x squared, and I'm going to subtract 0. So it's this y minus this y. So x squared minus x squared minus 0. Okay, it'd probably be helpful to do a little cleanup on this before you actually go to the calculator. Just less keystrokes. So 16 minus, there should be a square on that. 16 minus x to the 4th. Okay, and after all the computations, we're going to get 256 pi divided by 5. Let's take a look at some more volumes on the next page.